right. So our speaker today is Philipp Schlicht from the University of Vienna at the Kurt Research Center. And Philipp, it's great to have you. I personally wanted to hear you give a talk for quite a while now. And since you can't make it to New York, this is the next best thing. And Philipp will speak today about the recognizable universe in the presence of measurable cardinals. Philipp, go ahead.
Victoria, thank you so much for inviting me and for introducing me. I think I have about between 20 and 25 slides. It might not take so long, so please feel free to ask any questions or discuss if you want. And let me know if there's a problem with the sound. So the topic I want to speak about is about recognizable sets and the recognizable universe that we've been working on since a few years already. And I'm going to start introducing what this is all about because I don't think it's very well known. And mostly I will talk about this in the presence of measurable cardinals. So in a specific model, I want to determine the recognizable universe. So we started studying these sets a few years ago, and they originally were defined from infinite time computation. So I'll actually define it a bit later, how this came. And moreover, these sets are somehow tied with the implicitly definable sets that invented by Hamkins and Leahy a few years ago. I will also explain this in detail, actually. So there's a concept of a recognizable set of ordinals. It's a certain type of definition. And then you can generate a model of set theory from that, a model of a fragment of set theory from that we call the recognizable universe. The aims are to analyze this, in particular, assuming large cardinals, because we want to, right, so then maybe this model is more canonical, as we will see. And another type of problem is to fix a canonical in a model and determine the recognizable universe in that model. And this is a joint project with Philip Welch and in part with Marilyn Carl. So let me begin. So the usual definitions are not very absolute, right? So if you take a sigma 1, even sigma 1 definition in an ordinal parameter, if this parameter is uncountable, and you go to generic extension, you might the definition might not be absolute. So that's different from, say, projective. Projective definitions are absolute if you assume sufficient large cardinals. So the definition we're proposing here is always absolute. So you just take a set X of ordinals and you evaluate a certain formula in L of X. It's clearly absolute. And so specifically we ask, you fix an ordinal alpha and you look at all subsets of alpha, and for each X you evaluate phi in L of X, but you want to know that there's a unique one satisfying this. And then that we call recognizable. So even though it's defined in L of X, such an X does not need to be in L, because, for example, 0 sharp, or in fact any pi12 singleton is clearly definable in this way, because simply by Schoenfeld absoluteness, right? If you take the pi12 formula defining the singleton, will just work here. So and so maybe a different viewpoint of this is the lost melody phenomenon. If so Joel Hamkins gave this name to the phenomenon for infinite time computation. So I mean, you can think of a direct definition of X as a subset of alpha, but that's not what we're doing here. We're defining X as a singleton among all subsets of alpha, right? So it's kind of a implicit definition as opposed to explicit definition. And the corresponding phenomenon in computation is that you cannot compute a set, but you can decide it. So you can't actually compute the set, but if you're given the set, you can check whether that's actually the set. It's called lost melody because it's like hearing a melody, you forgot the melody, but when you hear it, you can definitely recognize it. And this phenomenon appears in many places, also in descriptive set theory, as explained that you might have a pi1 singleton, for example, but a real, but as a set of natural numbers, it might be much more complicated. Okay, so please keep this definition in mind. So just leave it for a few more seconds. The definition of recognizable. Let's understand the basic facts about these sets. The class of recognizable sets is not necessarily constructably closed. For example, take a cone real over L. This can never be recognizable because if it was, that would be forced by some condition P. And then any cone real extending that P would satisfy the same formula P, phi in its L of X. So you would suddenly have lots of reals satisfying this definition, and X couldn't be unique. But since zero sharp is recognizable, and zero sharp clearly constructs a lot of cone reals over L, well, therefore recognizable sets are not constructably closed. So it's natural to form their constructible closure. Let's call this R the recognizable universe. That I forgot to write down the definition. So R is by definition the constructible universe. All right. So a lot of basic questions to be here. What can we say in general about R and models of set theory? Can we prove that R is always a model for weak set theory? And which set theory is that? Can R have large cardinals, and which large cardinals can it have? Does it contain canonical inner models? Which ones? On the other hand, you can ask how variable R is, how it can be changed by forcing. Can you maybe put any given set into R by forcing over V?
Philipp,
yes?
could I just ask a quick question? So
yes, please.
When you say that, so one requirement of being recognizable was that X is, so to speak, the unique solution to L of X models phi of X.
Yes.
And you had this fixed alpha around. So do you mean for every
okay.
compared to all other subsets of alpha, it's the only one?
Yes, yeah. Thanks for getting back to this. So thanks for asking about this. Right, I mean, the way I set it up is you fix some alpha and we only compare subsets of that alpha. But it doesn't really matter because what I should really stress is that the formula has finitely many ordinal parameters. In addition, so those are not mentioned in the formula. So you could also just allow all sets of ordinals, but since phi might have a parameter alpha, and phi would just say the set is a subset of alpha. So it's actually irrelevant.
Okay, I see. Yes, I kind of skipped over that, and I was wondering. I see you allow ordinal parameters, right? Interesting. Okay, all right. Thank you.
Yes, thank you very much for clarifying this. So basically, one can try to prove that a lot of structure is contained inside of R, and then we can ask how what can be put into R by forcing. And I hope during my talk I will give you a little bit of insight in what we know. So we only have partial answers to all these questions. So I promised that I would explain how this concept originated from infinite time computation. So let's look at ordinal time Turing machines. Maybe you're more familiar with infinite time Turing machines, which is a Turing machine that runs on a standard tape, but with arbitrary ordinal time. So one can there also have a tape with ordinal length. I think these were introduced by Köpke. And so now you can, in the proposition I wrote here, you can ask, I mean, a machine can recognize something simply means you input a set of ordinals into the machine, run the machine and check there's some output. It's a natural number. And you, it could be yes or no. If that output is yes, then X is accepted. And the recognizable sets are precisely those that are accepted by such machines, where ordinal parameters are again allowed in the machines. So you can think of this as in the beginning, you write finitely many ordinals on the tape. Okay. So I don't want to say much more about that, except that this is actually where the definition came from. It's computationally something very natural to think of. And so again, so these machines can compute precisely constructible sets, so L, but they can detect much more because they could detect zero sharp and so on. I won't get back to this. Okay. The second connection I want to draw is to inner models defined from stronger logics. So there have been many such definitions where you do a recursive construction of an inner model, but instead of taking the first order definable power set as in L, you take some stronger logic or you allow some extra predicate. For example, you get hot if you allow second order logic, you can get Chang's model. And more recently, people studied L card. So you simply have a predicate for the cardinals in V, or L of Cof omega. So you have a predicate for the Cof omega ordinals in V. So while one can't really analyze hot because it can be changed too much by class forcing, let's say, the other three models in this list have been, there's a lot known about this. In particular, their theories are actually absolute, assuming sufficient large cardinals. And L card has been analyzed by Philip Welch, and he showed as a generic extension class or hyperclass generic of a fine structure model. So one knows really very well how this model looks like. And what I want to say here is that some such constructions lead to very nice models like L card that are much smaller than HOD. And so Hampkins and Leahy had this idea of defining another hierarchy using implicit definability, which I think they came up with. So a set X is implicitly definable over a structure M if when you add this X as a predicate to M, some formula defines X in the sense that there's X is the unique X prime satisfying phi X prime. So as you can see, it's pretty similar to recognizable, but here, well, it's actually a bit strange because you just add as X as a predicate. So if you think of X as a real, you would think of L with a real as a predicate, but you don't actually have L of X available. So it seems maybe a bit weaker than recognizability. In any case, they formed a hierarchy and define an inner model by simply iterating implicit definability through the ordinals. They call this the implicitly definable universe. And some questions they asked is, can this have some large cardinals, like measurable cardinals? Which large cardinals are absolute to this? And how can you change this by forcing? I'm talking about this first of all because there's a strong connection with recognizable sets that I will now mention in detail. So actually, recognizable sets and implicitly definable sets are essentially the same thing in the sense that their constructible closure is the same. I put another third definition that's quite natural, but I'm going to skip over this now. So the third definition is infinity without quantifiers and atomic formulas of the form alpha is in the set or not. So as I said, implicit definability looks a bit weaker, but it can be shown that recognizable sets can be coded by something implicitly definable by taking X and writing down a set that codes L alpha of X, showing that set is implicitly definable. So you show that a code for L alpha of X is implicitly definable. So this is not very hard. But remember, so the implicitly definable universe is not the implicitly definable sets, but this is iterated. So it's actually quite a different model. So what we've seen in this proposition that the recognizable sets and therefore the recognizable universe is a subclass of the implicitly definable universe. So as I said, the difference is R only has one step. You only form the recognizable sets and their constructible closure, while imp is iterated. So one can ask whether R is a proper subclass of imp. So I will give you one example later where this is true, an interesting model. And actually, I haven't studied this a lot. So I mostly studied R, and I think there are a lot of interesting questions and promising questions to use these results to study the implicitly definable universe as well. So let's get back to recognizable sets, unless there are any questions about implicit definability. So the main goals we have are, first of all, determine what can we say about R in general, about the axioms that are true there. And then we'd like to calculate R in some canonical inner models. And the ultimate goal is to assume large cardinals and determine the structure of R, say precisely what it is, if possible. And maybe this could be also used for the implicitly definable universe. So, well, understanding the basic axioms is quite simple, that these are things you can check. So our models, KP, cryptoplastic, except maybe for sigma 1 replacement. I'll talk about that later. It's closed under recursion if the recursion is sufficiently absolute. That's simply because it's constructively closed. So from its definition, one can easily check that the well-ordering principle holds, and it has a definable global well order. And also R in itself is again R. Then, so for a while we had the question whether R is admissible, and the candidate we came up with to show it's not admissible is L mu vector. Well, so the least model with an omega sequence of measurable cardinals, and I'll talk about that soon. Well, maybe let me say again. So this is the difference between R and imp. So the implicit definable universe is, because of its inductive construction, automatically a model of CF. So towards understanding recognizable sets in the presence of measurable cardinals, we want to start with some small models. So let's start with L of mu, where there's only a single measurable cardinal with a normal ultrafilter mu. And this is the least one. Then this is unique. So Kuhn's argument for this is essentially take L mu and L nu, so they have the same critical points. You take iterated ultrapros of both to some larger regular cardinal, where the images of the ultrafilters are, in both cases, the club filter, so they're equal. And then a Skoll-Imhall argument can be used to show that mu and nu were actually equal. So this is, for example, in Karnamori's book. So this can be rather easily used to see that so mu is recognizable from kappa. Well, I should say a code for an initial segment of L of mu. So L of mu has a canonical well order, and for example, a code for the L mu up to kappa plus with its canonical well order is recognizable from if you have a sufficiently large cardinals as parameter. I think lambda would work here. Because of the uniqueness, right? So you would you have this code for some L mu of alpha. Right, you simply need to check it's a model with a normal ultrafilter. Okay, and similar things can be done for finitely many measurables, and you will always need the measurables as parameters. So I'm not going to the details here. So I think the first very interesting case is L of mu vector, where these are infinitely many measurable cardinals. So I want to just fix this as notation. L mu vector will simply always denote this model. So we have a sequence kappa n of measurable cardinals, and mu n is a normal ultrafilter on kappa n. And L mu vector is least in the sense that the kappa n's are least. Again, this is a unique model. There's a unique model with this property. Then, so we want to, inside this model, we want to look at recognizable sets. And the first thing to notice that a recognizable set cannot construct a transitive model with an omega sequence of measurable cardinals. So in particular, a recognizable set cannot construct a large initial segment of L mu vector. And that's a rather easy argument that simply, so there's this interesting lemma of Cunan's that shows if you have omega many measurables and you take any ordinal, then one of so one of the ultrafilters, if you take the so they exist one of the kappa n, so that the single ultra power does not move that ordinal. So it has this as a fixed point. It's kind of a fixed point lemma. So so you can apply this to the parameters in the definition, then you will see that since the parameters are not moved, the set has to be in the ultra power, and well, that's a contradiction. So I don't know if that's clear. So when you take the ultra power with mu n, you lose mu n in that ultra power, but it would have to be there. Assuming this. Let me know if you have a question about this. So for the next few slides, I want to assume that V equals L of mu vector. So we work inside L of mu vector. So as we've just seen, the recognizable universe can't be everything. So what is it? So we didn't know for quite a while. It's not so hard to show that there's a lot inside R. So let's look at the nth measurable cardinal and initial segment of the universe up to kappa n or kappa n plus. So let's say we take the initial segment including the nth measure mu n. Then one can also show somehow by extensions of Cunan's argument that this an is recognizable. So essentially, n is simply supposed to be a set of ordinals that codes the model up to kappa n plus. So it codes the extender sequence of that model. as a fine structure model. So one can show this AN is recognizable by essentially similar arguments as cardinals that I give you. So this shows that in particular V kappa, so kappa is defined as the supremum of the kappa n, is so V kappa is a subset of R, and so Rn is defined as L of H kappa n plus. The union of those is an R. And then it seems natural to try to prove that R is actually the union of those models. So you would need to show that if you have anything, a recognizable set, then it is in one of the Rn's.
Could I just ask again? Sorry.
Yes, please.
So I just wonder what breaks down about this argument. I mean, essentially, the reason would be the uniqueness of this sequence, right? But the omega long sequence.
I didn't understand what breaks down where.
So I wonder what breaks down in this argument.
You don't have parameters, right?
Pardon?
Yes,
it seems like
breaks down because you only have finitely many. I didn't hear that, sorry.
I'm sorry, there is a lag somehow. Just go ahead.
Oh, so the argument breaks down for once you have omega many measurables, because for n measurables, you can simply have one parameter for at each measurable that makes sure they're fixed. If you have omega many measurables, you only have finitely many parameters, and then Kuhn's lemma tells you one of these alter filters has an alter power which fixes finitely many given parameters. Okay, so I mean, I was trying to, and the proof I actually gave you the proof on the previous slide that this doesn't work. But anyway, so the reason that you can't do the argument is because you don't have enough parameters. You're not allowed to have omega many parameters. I mean, you would need to say the nth measure sits at kappa n. Right. Thanks. So this was the argument. Yes, so I mean, this is a good point. So the being able to recognize these kind of LX structures breaks down precisely when you have omega many measurables. That's why L of mu vector is interesting. And so here by the last line, where do you know it does break down? So mu vector is actually not an R. So then the question is, what is precisely R? And I want to sketch how that works. So first of all, we need to define a given set from uniform indiscernibles. So by uniform indiscernibles, I mean I define AN to be a set that codes an initial segment of V up to kappa n. And by indiscernible for AN, I mean indiscernibles over L of AN. Okay, because we know AN sharp exists. And by uniform indiscernible, I mean an ordinal that's indiscernible for every AN simultaneously. And what we can see here is that if you have any set X that is in the union of the Rn, then it's definable in some Rn from a set in V kappa and uniform indiscernibles. So so similar as for zero sharp. So if you have a set in Rn was defined as L of An, then it is, as for zero sharp, it is definable from An and An indiscernibles. And here we want to know it's actually definable from uniform indiscernibles. And that's basically in induction. So I just claimed the first line in the proof. So since you can define X from ordinals. It suffices to prove the claim for ordinals. So take any ordinal alpha. There's an n which doesn't make sense, so that's just forget. So it's just any ordinal alpha. So we can assume A alpha is not a and indiscernible. But then we can define it from indiscernibles beta 0 to beta k below alpha and some above alpha. And the point here is that the ones above alpha are arbitrary. So those can be chosen as uniform indiscernibles. I mean, the way this definition works is the ones on top can be just shifted, can be chosen arbitrary for given this fixed definition. And then, but the ones below are smaller, so we can apply the inductive hypothesis. All right, so the next step we'll use an interesting result by Dehaenois, which actually Gunther told me about. So I realized at this point that at some point that something similar was needed. And so they observed that if you you have a single normal ultrafilter and you take the nth iterated ultrapowers for all n, and you form the intersection of the models mn, then the sequence of critical points of the iteration is perfectly generic over that intersection. And there's a really exciting result, I think, by Dehaenois on generalizations where you can do this through for any ordinal length, but there are different cases you have to look at. So depending on the cofinality, 3 different cases can happen. So why is this useful here? So we started with just some recognizable set X. We now define it from uniform indiscernibles that are called gamma 0 to gamma k. So the idea is, first of all, and there are 2 things involved. So, I mean, the definition has finitely many ordinal parameters. So if you take an ultrapower and you don't move those parameters, then, well, by elementarity, I mean, the image, you have the set X and you look at its image. By elementarity, X still satisfies the definition with the same ordinal parameters since they're fixed. But then X can't be changed because it's uniquely defined from those, right? So we have to look where the parameters are changed. But the parameters are now uniform indiscernible. So they're only moved. So when you take iterated ultrapowers with any of those omega many ultrafilters, they're only moved when you hit the next gamma I. So at all steps, alpha less than gamma 0, the parameters are not moved. But then when you hit gamma 0 is moved, right? So the critical step is there, and we can here use Dehaenois' result. So one of the results he showed that, so let's take this iteration of iterated ultrapower. Okay, I should be a bit more precise. So we're going to take, we have kappa many parameters, or kappa plus 1, and we're going to take kappa plus 1 many measures. We're going to iterate the first one in the first gap up to gamma 0, the second one in the next gap, and so on. And the critical thing to check is at step gamma 0, for example. And there, Dehaenois' result shows that, let's see. We already know that X is not moved before gamma 0. So up to now, it's in all the models. It's in the intersection of those models. And then Dehaenois showed that the intersection is, so the target model in step gamma 0 is how to say? So he showed that if you have anything HOD in the intersection of the models, HOD with parameters in the target model, then it is already in the target model. And here it's rather easy to see that X is actually HOD because it's recognizable. Okay, I hope this suffices as a proof sketch. And then you just need you also need a lemma about iterating, about commuting ultra powers that I'm just sweeping under the rug. Okay, but it's not a very long proof. That's essentially the proof. Any questions?
Yeah. Isn't there a unique least mouse projecting to omega with countably many total measures on its sequence? And why doesn't that end up being recognizable?
Well, it is recognizable by, so I'm skipping over these results because this is more Philipp Welch's expertise, who's here, I think. Philipp, are you there? Okay, yes, he's there. So,
I could make a comment if you want. Do you want me to make a comment?
Well, I'll first say something, then let you comment. This mouse sits,
I can't hear you.
It's countable, right? Oh, I see. So the mouse you're talking about is countable. Can you hear me, Gabriel?
Yes.
Yeah, now I can hear you. Sorry.
Okay.
I have bad internet.
Okay. So, the mouse you're talking exists in L of me vector and it's countable, right? So,
yes.
Right. And we already know that everything in V kappa is in R. So this clearly also in R. So I'm not sure what's exactly your question. So it is in R in this model. And was that your question? And maybe Philip, you can comment if you.
Why is the mouse in Rn for some n?
I just sent an answer.
So I see. I didn't see that. So here we already said that. So that V kappa is contained in R. So this mouse in V kappa. So AN codes the whole initial segment of up to kappa n. So it codes V kappa n. So you recognize something much larger. Does that answer your question? I didn't see the chat also.
I think I misunderstood what Rn was. Yeah.
I see. So right. So we have a sequence kappa n of measurable cardinals with supremum kappa. And so mu n is the measure on kappa n. And so Rn contains, well,
yeah, I get it.
H kappa n plus already.
Yeah. I thought Rn was the minimal proper class in our model within measurable.
Okay, yes. Sorry, I should have been more precise about that.
I should have paid better attention.
Is that fine, Philip? Should I continue? Because
Yes.
I didn't see the chat.
Yes.
Okay,
fine.
thanks. Okay. So we've seen a sketch of both directions. What is R here? So I mentioned we were interested whether R is admissible. Actually, we didn't know for a while whether maybe R is always admissible. So in this model, it turns out it's not admissible. So it doesn't satisfy sigma 1 replacement and sigma 1 collection. It does satisfy those if the domain of the relational function is an element of V kappa. That I'm not going to skip the argument. I don't think I want to prove anything more. So sigma 1 replacement does hold when the domain is an element of V kappa. So it does hold for small functions in domains. I see, but let me skip here.
Philipp, sorry, what is n on the slide?
This is a typo because it's some old notation I had for R actually. On which slide? This one?
The previous, no, the one before.
Yes, I'm very sorry. It's a typo.
This one.
And there's an N. Is there an N?
The other one. Next one. Yes, there's an N. I was.
Oh, I see. That's R. Yes, I'm very sorry.
Okay, thank you.
Thanks. So here's Philipp's argument for the failure of admissibility in LME vector. So we're going to look at a sequence of mice in increasing order, in the mouse order where, so mouse M is below mouse N if means that when you co-iterate them, the target model of N will be longer, will be extend that of M. So that's a well order on mice. And we're going to look at only the mice in V kappa, which in particular, there are only set many. And we need to check that the enumeration of those is a sigma one definable. So we want to know it's given by a sigma one recursion. In other words, the first mouse, which is 0 sharp, is given by a sigma one definition. Could be in some parameter, I think it's kappa here. Then when you've given 0 sharp, you can find the next one by uniform sigma one definition and so on. And if you already have a sequence of mice, you can find the next one by a sigma one definition. So I only want to say that two lemmas are involved here. The first one is that attributability is absolute as folklore result. So if you have a transitive model of ZFC minus that contains omega 1 as an element and a certain pre-mouse, then omega 1 plus 1 attributability of that pre-mouse is absolute between this model and V. And so we need this because the sigma 1 formula will say there is a certain transitive set of size, at least omega 1, containing the function up to this point. And it contains some other mouse, and it can see this is iterable, which should be correct. And the second thing we need is that such models should be able to see whether there's a gap or not between. So if you have a sequence of mice and one on top, the model should know whether there's something between or not. And that's a particular argument here that I think Philip Welch and John Steele did in a more general, for a bit more general mice, but I'm not sure how far this goes. Certainly not very far, not to wood in cardinals or something. So in any case, someone shows this recursion is sigma 1, and but I mean, remember that the L of AN, so these are pre-mice that mice, they're initial segments of the universe. The union contains V kappa, and they all appear in this enumeration. So if R was admissible, you could take, you would have the range of this function. You could take the union, and so V kappa would be contained in the range of F. But it's not, because we know it's R. It doesn't contain V kappa as an element. Okay, so the counterexample to admissibility comes from enumerating the mice in V kappa. So I want to quickly draw a conclusion about the implicitly definable universe, and where you can also see the difference between R and imp. So we've seen that R is the union of L of H kappa n, where kappa n are the critical points, the measurable cardinals. But so imp will be all of L of mu, simply because it's a model of ZF. So so the measures mu n are themselves in R, but if you have a model of ZF, you see the sequence, and the union has to be in there. So mu vector is in imp. So here R does not equal imp. Okay, so in the last maybe 5 or 10 minutes, I want to go to a more general question. Well, first of all, I don't think we've tried to see how far this goes. Well, considering beyond LMU vector some bit larger models, I think in general the techniques should work up to some point. So something interesting happens at Wood cardinals that I want to talk about a bit. So these are all partial results. We don't know the full answer. So let's call so the least fine structural Burrow model with the Wood cardinals called M1. And so what you can do is take its least measurable cardinal, and so there's a unique normal measure there, and just iterate this odd many times, form the iterated alter power. So the resulting model, I guess, doesn't have any measurables, right? Because you took the least measurable and you always shifted it higher up. So what we know here is only for subset of countable ordinals. So a recognizable subset of countable ordinal is always in this model M infinity. So this is another barrier what you can recognize in general, right? And this has a converse. So essentially these are equal. So if you have so actually M infinity is contained in R. This is what the next result shows.
So I have another stupid question. If M infinity has an inner model with infinitely many measurable cardinals, so I thought that you had a theorem that couldn't be measurable from a recognizable set.
Well, yes. Thanks for the question. I'm not sure. I'm not really sure. Thanks. Yes, I need to look that up. Maybe I got the statement of the previous result wrong.
Okay, thanks.
Thanks. I need to check that. Thanks. Right. I mean this is certainly true. So this result. So I must have gotten the previous statement wrong. Let me check later. Thank you so much. So let me disregard this problem for a moment. Then for subset of countable ordinals, these two tells everything about R. But for subset of omega 1, we, for example, know it's consistent that this equivalence holds as well. So the next theorem here. So I might as well say that, I mean, my conjecture is that M infinity simply equals R. But so my goal is to prove that M infinity equals R from a proper class of Wood cardinals or possibly stronger assumptions. Okay, so this is my goal. And I think these two first theorems are go into that direction. They show this is true if you look at subsets of countable ordinals. For omega 1 consistent, it also follows, for example, from certain forcing axioms. This equivalence holds for omega 1. Actually, I don't know anything for subsets of omega 2. It's a different thing. So I want to mention, so I'm working on partial results for subsets of omega 1, and I just want to mention one of them. So let's assume that H omega 2 is closed under M1 sharps. Then, and we make the additional assumption that you have a subset of omega 1 that's recognizable from only countable ordinals and V cardinals. So we restrict the parameters. Then one can show it's in M infinity. So it's also pretty close. And okay, I'm already at the open questions. So as I said, the main goal is really, so we know in LMU vector, we know precisely what is R. Can you prove only from large cardinals assumption, can you determine R? then I think it would be really interesting to study the implicitly defined universe. So I haven't really thought about it at all, I have to say. And it seems to be larger than R. And so since I admitted my conjectures that R equals M infinity, so I also think that imp will be larger. For example, one could try to show it does it contain M1. So M1 is larger, right? It contains its first measure, which is gone in M infinity. So the first step is to show that this first measure is an element of M, which seems reasonable. And so then there's an interesting problem that I've asked a lot of people over for several years that is also related to these questions, because it's the question of unique generics. Because if you're in a model V and, for example, over L, you have a unique generic, then this is always recognizable. So by unique generic, I mean this happens for certain Switzerland trees. When you force over L, you force and you add a unique branch, then in the extension you can recognize that branch as simply as the unique branch. So the question I have had for quite a while is, let's make a large cardinal assumption. For example, zero sharp exists. And I want to show, and I strongly conjecture that there is no unique P generic over L for any forcing P now. So if you have any ideas, please let me know. And as I said, this is closely related to recognizability and implicit definability. And I think it's a very interesting question in itself. And I think it seems very hard. I've also asked Wood in this, for example, and other people. And so let me end with a few references to literature. So the paper of Dionnois that I use called Iterated Ultrapowers and Prickle Forcing. It's quite an amazing paper, I think. And so Hampkins and Leahy wrote this paper called Algebraicity and Implicit Definability in Set Theory. And there's a kind of follow-up paper where they answered some very interesting questions from that paper by Groshek and Hampkins in 2019. It's also quite recent. And so our paper is from 2018, and well, then we have this work in preparation. Okay, let me end here. Thank you very much for your attention. Thanks.
Thanks very much, Philip. We already had a bunch of questions. Are there more questions for Philip?
I have more like a comment/question.
Mm-hmm.
Because I mean, you use this model M infinity, which is just M1, and you iterate out the first measurable cardinal. So what presentation of M infinity do you use? Because I mean, there is a nice characterization as in a lower part model in a model theory. Are you using this or?
No, I'm just using its definition as, you know, an iterate of M1. So can you just tell me what the characterization is, maybe? Or maybe I ask you later if it's too complicated.
Yeah, I mean, I wrote you a WhatsApp message already.
So I don't know this characterization, so I'm very interested. Thank you.
Yeah,
okay,
but I mean,
thanks. Thanks. I'll ask you.
Mice that keep projecting to omega, and this builds a level, and then you keep stacking that one on top of the other. And that's nicely definable.
Over what?
You look at all mice that project to omega, union in the map, and then you take all mice projecting to omega that extend this part. You keep doing that, and you haven't.
Don't you get?
But this is nicely defined.
Oh, I see. You mean minimalities no Wood cardinals, or
yes.
Or no extenders above
Wood
cardinals.
I mean, you can say something like K1 2 equivalent, and you can put a definability condition on the iterability and stuff like that.
Okay. Okay, this might be useful for recognizability if you have absolute iterability condition like pi1 2. Anyway, I'll get back to you. Thank you very much.
Sure.
I have a question a little bit off from the main topic of your talk. So I'll be happy if your answers just go look at this paper. So you're interested in R in the presence of large cardinals. Is it known how R behaves in the absence, say in like L, how R behaves?
Yes, I see. Thanks for for asking this. So, I mean, basically, I think there are two settings. I looked at the setting with large cardinals, and in like kind of smaller models, like forcing extensions of L, the thing is, right, I mean, you're totally right that when, and this is a very different picture because you can just change R as you like, basically. So for example, if you take any set generic extension of R of L, then you can find a further generic extension where any given set you had was now becomes recognizable.
Okay, so it's very malleable.
So it's very flexible, malleable. Yes, that's a nice word. Of course, I mean, this for generic extensions of L, so these are kind of models without large cardinals.
Okay, but does it,
Thanks.
can you say something about the theory in that, kind of a follow-up? So you can add lots of sets. Do you know that it's not going to satisfy KP, for example? It won't be admissible.
I see. Okay, that's a very good question. I haven't thought about it, so I'm just gonna.
I guess I'm thinking analogous to like set
does it
theoretic
always
geology.
KP and
Yeah.
Why is this analogous? I mean,
sorry, no, sorry. I'm saying my thought is this is analogous to like stuff in set theoretic geology, like the mantle you can make whatever you like, but it's satisfies a nice theory.
Okay, yes, thanks. So I mean, my if I can just make a wild guess, it's that KP also fails in generic extensions of L, but I don't have any evidence for that. So thank you.
You can't make the recognizable sets be everything and then get ZFC.
Well, you can do that in generic extension of L. For example, add a pi12 singleton, then R will be everything. But that probably doesn't answer your question. And also L of, as I mentioned, L of mu has itself R as V in L of mu. So in small models, like L of mu or some generic extensions of L, R can be everything. Right. I mean, I guess maybe.
No,
not sure which other models. Maybe you have some model in mind that you think.
I think I didn't understand whether the question being asked was universal or existential. Like, are there generic extensions of L in which the recognizable sets aren't admissible? Was that the question?
I mean, I was interested in kind of in both questions.
I mean, of course, there are also many extensions where it's just L. So when you do homogeneous forcing, then I mean, hard will be L, and therefore, so R is also contained in hard. Maybe I should have said that. So, and in those cases where hard equals R equals L, but then if you take some very inhomogeneous forcing, you can make R be very large. But so I'm not sure which. Did you have another question in mind about that?
Me?
Gabriel?
No.
Okay, thanks.
Thank you for the answer.
Okay, thank you for these ideas and questions.
If I can make, it's Ken McAloon, if I can make a historical remark about the Patrick Doranois paper that you referenced. That when he first came into my office in Paris with the proof that as you iterated the ultra power on the measurable cardinal out to omega, the intersection model didn't satisfy the axiom of choice. It was a stunning result, and it made me think at the time that Dana Scott could have proved that when he proved that V equals L was false if you had a measurable cardinal. But that result was just hanging there for all those years. But in that paper, he shows, in fact, it is a forcing result underneath it all, because there are all these trickery sequences kicking around.
I see.
Yeah, but
I see. Thanks for that comment. Yes.
Yeah, but Patrick then he's passed now. But Patrick then went on to become an expert later, using the combinatorics of measurable cardinals and large cardinals, become an expert on braid theory. Group theory.
Yes.
Braid groups. Yeah.
So let me add that I think this paper is also very very difficult and non-trivial. So because you said somebody could have found this early, yes, but also I mean the results are really proofs are very, very interesting.
Yeah, he was a good combinatorist, Patrick.
What model did you say doesn't satisfy the axiom of choice?
You take the ultra powers on a measurable cardinal and go to the limit. You take the intersection model rather than the limit model.
If you do this omega-1 many times, it's not a model of choice.
Okay, that's what I think.
If you do it omega times, you get a model of choice, of course.
No, the model of the choice fails in the omega intersection.
No, in the omega intersection, it's a prick reinforcing extension of the direct limit model.
Not the limit model, yes, maybe, but not the intersection model.
Oh, I think it's the case. Like if
just
you
set theoretic intersection.
Yes, that's the prick reinforcing extension of the direct limit model.
Okay, then my memory is shaky. That's not unusual.
It depends on how long the sequence is, how long you iterate. If you do it omega-1 many steps, I think it's not a model of choice. But if you do it omega steps, it is a model of choice. It's a very good analysis. Okay. Are there any other questions? Great. Okay. Well, thank you. Great talk.